Hello, and welcome to Ask Dr. Dawn. The opinions expressed in this program are those of the speakers, and this is a program intended for education and entertainment. It should not be construed as a substitute for a medical consultation. We're going to start this week's program talking about psychiatry and inflammation and autoimmunity. It's quite a ride, so I hope you'll enjoy it. There's a dreadful tendency in medicine to whittle away at a presentation of something mysterious until it fits in one of the boxes that you know about. When the presentation is unusual and doesn't fit any of the boxes, there is a tendency to dismiss it as hysteria or some sort of psychological manifestation. This is a real cognitive error in medicine, and it happens all the time. Today we're going to talk about such a series of cognitive errors and what a closer look at this phenomenon is teaching us about mental illness and how much of it may actually be triggered by infectious disease and autoimmunity. Let's start with the story of a little girl named Jessica Wheaton. She was only 12 years old when she began having tics, involuntary little movements of her head and her lips. Over time, this condition worsened until she was having whole-body fits that looked to her parents like epileptic seizures and being rushed to the hospital. But her local hospital was dismissive, suggesting she had anxiety, a mental health condition, and that she was probably spending too much time watching videos on TikTok. Her mother describes the experience as belittling. In fact, Jessica had an autoimmune disease brought on by a bacterial infection with Streptococcus. The condition is known as Pediatric Autoimmune Neuropsychiatric disorders associated with Streptococcus. There are also just pediatric autoimmune neuropsychiatric disorders that are not associated with Streptococcus. And the existence of these has filled up hours and hours of seminars that I've attended over the last few years, because this really does go to a mechanism for mental illness that is transforming the way we look at the brain. Now, little Jessica is not alone in having a dysfunction in the brain mistaken for one of the mind. But slowly evidence is accumulating that an array of infections can, in some case, trigger conditions that we would normally term as psychiatric, such as obsessive-compulsive disorder, tics, anxiety, depression, and, most frightening of all, even psychosis. And infections are just one small piece of the puzzle. It's increasingly clear that the infections are triggers for inflammatory disorders and metabolic conditions that can have a sizable effect on mental health. This is a blind spot for psychiatrists. They rarely look for any of these factors. And psychiatry has a lot of problems. A revised understanding of psychiatry could have profound consequences for millions of people with mental health conditions that are currently poorly treated. For example, over 90% of patients with bipolar disorder will have recurrent illness during their lives. And in children with obsessive-compulsive disorder, over 46% do not achieve remission. Some 50 to 60% of patients with depression eventually respond after trying many drugs, meaning that 40 to 50% do not. We need to cultivate a deeper understanding tied to the biological fingerprints that we might find in a laboratory test, and to a greater willingness to not stop at diagnosis and drug, but move deeper into source of the issue, something that could be said for many of the current medical treatments. I almost said medical damages to current diseases like hypertension and irritable bowel. But let's stay on psychiatry and roast them for a little bit longer. Psychiatry has a problem. In order to be considered a science, it first has to describe the problem. And the problem, of course, is quite variable across individuals. So it's really not diseases. it's syndromes, patterns of symptoms that psychiatry is forced to organize into a sort of taxonomy. A bit like Linnaeus coming up with how do we classify plants and animals, psychiatrists have come up with something called the Diagnostic and Statistical Manual for Medical Disorders. It emerged first in 1952 and has undergone numerous revisions as social and political forces have changed society and its understanding of what constitutes mental illness. For example, homosexuality appeared as a mental illness in early versions of the Diagnostic and Statistical Manual of Mental Disorders. And I think at this point in our cultural understanding of this entity, it is a healthy variant of quote unquote sexuality and not a mental disease. Now, it's been helpful from the sciencey standpoint because it allows us to be consistent in our diagnosis. So we know, for example, that if we're going to test a drug on people with depression, that these people have met certain criteria listed under depression in the DSM, whatever it is, and that allows for science to occur because now you have people who belong in the same cohort, so you can test your drug on them. One of the dirty little secrets of psychiatry is that there's so much overlap between the symptoms of, say, depression and anxiety that it's possible that these don't even represent separate categories of illness when you get down to the nuts and bolts of what's going on. And at the same time, depression and anxiety come in many different subtypes. You get panic disorder with or without agoraphobia, for example. This is a distinct diagnosis, but is it distinct in terms of its cause? Well, there you get into another problem. Part of our problem is that when we try to identify patients to test in drug trials, we have a lot of trouble in various forms of mental illness in making sure that we're getting people with the same thing, and therefore one hopes the same metabolic issue in the same study. A lot of potentially good therapies probably fail because we haven't done a good enough job of identifying the cohort that should be studied. You know, we're not stupid in medicine. We know this isn't working really well. And in 2013, the National Institute of Mental Health thought, in the wake of the whole genome being read, that we would go looking for genetic sources of mental illness to try to identify the distinct categories more carefully. A lot of money went into basic research on disease processes in the brain, hoping to directly connect genes to the behavior. Something like 20 billion of research money was sent off in that direction. That's a lot of research money. And it failed spectacularly. Most of the genes uncovered had tiny effects. It was, as Alan Francis, professor of psychiatry at Duke University, said, a fascinating intellectual adventure, but a complete clinical flop. So genes are not the answer. In fact, many different conditions, such as schizophrenia, attention deficit hyperactivity disorder, anxiety, and autism, can all be triggered by the same genetic disorder, 22q11.2, which is caused by a small piece of chromosome 22 being deleted. Now, a major shift in psychiatry is coming because now we have the metabolome, the idea that we can look at small molecules floating around in the bloodstream, floating around in the spinal column, and maybe infer something about what's actually going on at the nuts and bolts biochemical level in individuals. And in cases like PANDAS that I started out talking about for this presentation, we're becoming aware that some of these mental health conditions may actually have triggers and roots which need to be treated as medical conditions rather than lumped into psychiatry. A key pivotal moment came in 2007 when work at the University of Pennsylvania showed that 100 patients with rapidly progressing psychiatric symptoms or cognitive impairments actually had an autoimmune disease. their bodies were creating antibodies against key receptors in nerve cells known as NMDA receptors. These are excitatory receptors in the brain. These antibodies lead to brain swelling and can trigger a range of symptoms including paranoia, hallucinations, and aggression. The disease was dubbed Anti-NMDA receptor encephalitis. Most important of all, in many cases it was treatable by removing the antibodies from the bloodstream using plasmapheresis or suppressing the formation of these antibodies using immunotherapy drugs or steroids. Studies of patients having a first episode of psychosis have found that between 5 and 10% of these individuals have brain-attacking antibodies in their system. It now seems likely that in rare cases, OCD, obsessive-compulsive disorder, can be caused by the immune system too. This is one of the more common conditions that are seen in PANDAS, that streptococcal inflammatory brain disorder that we started off talking about. But it is sometimes found in adults. There's one case of a 64-year-old man spending an extraordinary amount of his time obsessively trimming his lawn, only to look back on his behavior the next day with feelings of regret and guilt. Researchers found these symptoms were being caused by antibodies attacking the neurons in his brain. Most recently, a researcher named Belinda Lennox, head of psychiatry at the University of Oxford, has conducted tests on thousands of patients with psychosis. She has found increased rates of antibodies in the blood samples of about 6% of patients, most of these antibodies targeting the NMDA receptors. She says it remains unknown how a single set of antibodies is capable of producing the various clinical presentations seen, ranging from seizures to psychosis and encephalitis. But remember, NMDA is the receptor that notes glutamine. Glutamine, as a neurotransmitter, is broadly excitatory, and its contrary neurotransmitter, the yin to its yang, is GABA, which receptor Valium and the other benzodiazepines attach to and stimulate. It's not known why these antibodies are made or how they get across the blood-brain barrier, but they apparently do, and she has found that they preferentially stick to the hippocampus, which would explain how they affect memory and lead to delusions and hallucinations. Dr. Lennox says a shift in medical thinking is needed to appreciate the damage that the immune system can do to the brain. The million-dollar question, she says, is whether these conditions are treatable. She's now running trials to find out more about how she might treat them. Work on patients with immune-driven psychosis suggests that a range of strategies, including removing antibodies with plasmapheresis and taking immunotherapy drugs or steroids, can be effective treatment. Another important recent discovery is that metabolic disturbances can also affect mental health. The brain is an energy-hungry organ, and metabolic alterations related to energy pathways have been implicated in a diverse range of conditions, including schizophrenia, bipolar disorder, psychosis, eating disorders, and major depressive disorder. At Stanford University in California, where there is a metabolic psychiatry clinic, patients are treated with diet and lifestyle changes along with medication. One active area of research at the clinic is the potential benefit of the ketogenic diet, in which carbohydrate intake is limited. This diet forces the body to burn fat for energy, thereby creating chemicals known as ketones, which can act as a fuel source for the brain when glucose is in limited supply. Kirk Nyland, head of neuroscience for the Brasuski Group, an American charity that funds brain research, says 13 trials are underway worldwide looking at the effects of metabolic therapies on serious mental illness. There have long been reports that the ketogenic diet can be effective in children with seizures. It's also been shown to have benefit in some cohorts of children with autism and in adults with dementia related to either Parkinson's or Alzheimer's disease. Now, these reports and case studies are getting some real money behind them, and solid scientific research is being done, finally. The preliminary reports have shown large group of peoples responding in an incredibly meaningful way. There are people that have failed drugs, talk therapy, transcranial stimulation, and maybe even electroshock therapy, who are getting better on ketogenic diets. He says he keeps meeting psychiatrists who have come to the metabolic field because of patients whose low-carb diet were followed by huge, remarkable improvements in mood. So results from randomized clinical trials are expected in the next year or so. I'm a little skeptical because I can't imagine how you can do a double-blind placebo-controlled trial on something as difficult as the ketogenic diet. But I don't know. Maybe we're going to have people just drink flavored smoothies for their entire duration of the trial. I'm having real trouble with how you're going to get a good placebo on that. It's not only the understanding of the immune and metabolic systems that's improving. Vast quantities of data are now being parsed with unprecedented speed, sometimes with the help of AI, to uncover connections previously hidden in plain sight. Now, here's some old news masquerading as new news. In early October 2023, UK Biobank, a biometrical database, published several data revealing that people with depressive episodes had significantly higher levels of inflammatory proteins, such as cytokine, in the blood. A study last year found that about a quarter of depressed patients had evidence of low-grade inflammation. This could be useful to know, as other work suggests patients with inflammation respond poorly to antidepressants. I just have to throw in that this is something I heard about 10 years ago at a functional medicine conference. So like I said, it's new old news to me, but a lot of things that seem too crazy or outlandish to make it into standard medicine show up in functional medicine a few years or maybe a few decades before they are generally adopted by the somewhat conservative medical academy. But at least more innovation is underway. A number of researchers are exploring different ways of improving the diagnosis of ADHD, classifying patients into a number of different subgroups, which is probably true. In 3 separate announcements in February of this year, several different groups announced the discovery of biomarkers that could predict the risks of dementia, autism, and psychosis. The search for better diagnostic tools is also likely to be accelerated by the use of AI. There's one firm called Cognoa is using AI to diagnose autism in children by focusing on video footage of their behavior, sidestepping long waits for clinicians. Another outfit, the Quantitative Bioscience Institute, QBI in California, has used AI to create an entirely new map of the protein-protein interactions and the molecular networks involved in autism. This is really getting into a deep dive of the mechanisms at work in this devastating condition. But we still face a lot of problems in psychiatry, and many of psychiatry's problems could probably be resolved by relaxing the distinctions that exist today between neurology, which studies and treats physical, structural, and functional disorders of the brain, and psychiatry, which deals with mental, emotional, and behavioral disorders. Dr. Lennox finds it extraordinary that the treatment options differ so completely if a patient ends up on a neurology ward or in a psychiatry ward. She wants antibody testing to become more routine when someone presents with a sudden post-viral mental illness or even a sudden mental illness that does not get better with standard treatments. Another senior researcher at King's College in London, Thomas Pollock, says MRI scans should probably be used on patients after their first episode of psychosis, as in 5 to 6% of patients it would change the way they are treated. MRI scans have the ability to identify inflammation just by looking at the biochemistry of the brain. I want to digress for a moment here and just mention that the putative father of psychiatry, Dr. Sigmund Freud, actually studied neurology with a very famous Dr. Charcot, who, among other things, has a medical condition called Charcot foot named after him, but who was also very interested in using hypnosis to treat neurological disorders. And that's where Freud learned to do hypnosis. This rift between neurology and psychiatry is greater in Anglo-Saxon countries. In Germany, and presumably Austria, psychiatry and neurology are much more integrated, with neurologists training in psychiatry and psychiatrists doing a year of neurology as part of their training. This makes it much easier for investigational work to be done, and I think we can expect that a lot of the best work is going to come out of Germany and Austria. There's a Dr. de Bartz van Eltz in Germany, no less, who says he offers most patients with first-time psychosis or other severe psychiatric syndromes an MRI of the brain, an EEG, lab tests for inflammation, and a lumbar puncture to find evidence to support the different treatments of some patient. Now, we know we're in Europe. Dr. de Bartz van Eltz goes on to say the price tag is only about €1,000, which is no more than the cost of hospitalizing a patient for 3 or 4 days. So it's a very good value for money. Well, given that the price of hospitalizing a patient for 3 or 4 days in our country is easily 10 times the cost of an MRI and EEG and lab tests for inflammation and a lumbar puncture, I think we should seriously be looking at that, especially since mental health hospitalization is extraordinarily expensive and generally takes a person away from their community because of the paucity of facilities available in our country. So maybe one day all of this work will put psychiatry and its patients on a firmer footing with more accurate diagnosis and more appropriate treatment. And it's already offering validation for some of those who the field has failed. Another group that I really want to point out are those with myelitis encephalitis chronic fatigue syndrome, a post-infectious condition that comes with a series of cognitive problems, attention and concentration deficits. People were often dismissed as malingering or depressed, but new work suggests that this is both an immune and a metabolic dysfunction, and as such can be addressed in a much more meaningful way. I'm feeling a little more optimistic about fewer cases being dismissed as crazy when they are in fact caused by curable biological manifestations. We have to stop covering up the symptoms and go to the root problem and fixing the problem where it's being generated. That's the goal of functional medicine in general, and it's nice to see it starting to get some traction in psychiatry. In the light of our previous discussion of autoimmunity in the brain, this seems to be a good follow-up article. This comes from Nature Journal, and it's an overview of curing autoimmune disease by reprogramming the immune cells themselves. To learn more, we have to go back to 2001, when immunologist Per Santamaria was exploring a new way to study diabetes. This is type 1 diabetes, in which the immune system destroys the cells in the pancreas that make insulin. Working in mice, he and his collaborators developed a method that used iron oxide nanoparticles to track the key immune cells involved in the disorder. At that time, Santamaria was working at the University of Calgary in Canada, and he came up with a bold idea. Maybe he could use these particles as a therapy to target and quiet, or even kill the cells responsible for driving the disease, typically T cells producing an autoimmune attack against the insulin-producing islet cells of the pancreas. It took 2 decades of experimentation before Santamaria's technique was ready to be used on people. Dr. Santamaria is not alone. It's been at least 50 years that researchers have been trying to find ways to tame the cells that are responsible for autoimmune disorders like type 1 diabetes, lupus, and multiple sclerosis. Most of the approved therapies for these conditions work by suppressing the entire immune response. This may alleviate symptoms, but it leaves people at elevated risk for infection and cancer. So for decades, immunologists have been hoping to learn how to restore what's known as tolerance, the immune system's ability to ignore antigens that belong to the body and should be there, while appropriately attacking those that don't. In some cases, that may mean administering the very antigens that the rogue cells are trained to attack, a strategy that can sometimes deprogram the cells and dampen the autoimmune response. This is, for example, one of the strategies that's used in sublingual immunotherapy to treat people with strong food sensitivities like peanut allergy, giving small but increasingly greater doses of the antigen, not so much as can cause a large response, but just little by little exposing the immune system to it, has the effect of bringing into play a third category of cells, which are the suppressor T cells that suppress the immune response. Other research has tried to selectively wipe out the problematic cells, targeting them by their surface antigens, or introduce suppressive immune cells that have been trained to target them. So fight the rogue immune cells with immune cells that are with other immune cells. Now, one approach that relies on engineered immune cells was used to treat 15 people with lupus with surprising success, with one person remaining symptom-free for more than 2.5 years. Rheumatologists generally agree that the therapies we have for autoimmune diseases are terrible. They don't always work, and even when they do, improvement is modest, and there's almost always a downside that causes problems over time. We need to think about cure. So let's go back and let's do a little lesson in Immunology 101. The immune system is known for its role in attacking pathogens, but it has another equally important job, which is knowing when to quit, when to stand down. If immune cells see the body's own tissues as a threat, they can cause harm. And in the case of PANDAS, which we were talking about earlier, it's very analogous to rheumatic fever or streptococcal kidney disease, where a antigen, a surface marker on the streptococcal bacterium, stimulates the immune system to make antibodies against it. But unfortunately, these antibodies cross-react with a body tissue, whether it's the heart valve or the kidney cell of the glomerulus or the NMDA receptor in the brain. And it's this cross-reactivity that causes the immune cells to continue to be made and reinforced because their target is still present, even though it's a mistaken identity, what we often call a molecular mimicry error. So the arm of the immune system engaged in targeted attacks consists of cells called lymphocytes. Lymphocytes can differentiate to form T cells, which recognize and attack foreign or discarded cells, or they can differentiate it into B cells, which produce antibodies and support the immune system in other different ways. When we vaccinate someone, we produce both B cells and T cells against the disease, particularly if that disease is a virus. The B cells produce antibody for a while and then go dormant, and how long it takes them to stop producing antibody varies quite a lot from disease to disease. Hence the ambiguity and great variability of when a person needs a booster shot on a standard vaccination. So early in the development of the immune system, cells undergo a process to weed out those that target the body's own tissues. This largely takes place in the thymus, which is huge in infants. It performs introductions. Hello, immune cell. Oh, look, you want to attack a heart valve. No, we're going to downregulate you. You don't get to divide anymore. Sayonara. And the microbiome is involved in this somehow, probably because babies have quite leaky guts. And so fragments of the lipopolysaccharides of the surface of the bacteria are circulating in the bloodstream, and the thymus recognizes those as benign, the so-called probiotics, and they help assist with this tolerance phenomenon. That's why establishing a healthy microbiome in childhood is so important. It strengthens the immune tolerance in ways that we do not yet fully understand. The body also has a backup system called peripheral tolerance. This eliminates or deactivates wayward cells or turns them into regulatory T cells, which suppress the immune response by preventing other cells from attacking. That's what happens with the sublingual immunotherapy. And in autoimmune disease, both of those mechanisms, both the central and the peripheral tolerance, break down for reasons that are not understood, and the immune system starts attacking antigens found on the body's own cells. Sometimes, often probably, it's triggered by a foreign protein with a close resemblance, and it just doesn't turn off properly. In multiple sclerosis, for example, the body attacks the myelin sheath that insulates nerves. It's thought that the virus that causes mono, Epstein-Barr virus, may be implicated in a molecular mimicry way with multiple sclerosis. In celiac disease, gluten triggers the immune system to attack the intestinal lining, but the intestinal lining is not the only place that gets attacked. The immune system cross-regulates or cross-identifies other damaged fragments, tissue transglutaminase, which is present in the gut after it's been attacked by the gluten antibodies. The system is so revved up it starts to attack the fragments of the tissue transglutaminase. This leads to a very high frequency, as much as 70%, of thyroid damage in people with celiac due to molecular mimicry and the fact that the thyroid has high numbers of tissue transglutaminase on its surface. If scientists could calm or eliminate the malfunctioning cells, restoring tolerance to specific antigens, they could directly treat the disease without hampering the immune system's ability to respond to real threats. Early efforts focused on administering large quantities of the problematic antigen in an attempt to exhaust or deactivate the immune cells that recognized it were tried. Many groups have tried this form of desensitization. It can work, but the antigen must be introduced in the right way to boost tolerance rather than activate immunity and make it worse. Antigen-specific therapy, the name of that field, is in its infancy, but finding the right antigen is tricky. Some autoimmune diseases are caused by a reaction to just one, but many conditions, like multiple sclerosis, diabetes, and rheumatoid arthritis, to name a few, the body develops an immune response against several antigens through a phenomenon called epitope spreading. I was just alluding to that in reference to the gluten antibodies eventually leading to damage to the thyroid. Researchers could try to work out all the antigens involved, but it's a tall order because the list may vary from person to person. Well, what else could you do? Well, maybe you could find the master switch that, when flipped, turns off the autoimmune response while leaving the immune system intact. Santa Maria, remember we were talking about him at the beginning with iron as a marker? His team's iron nanoparticles, which he calls navicims, are decorated with proteins called major histocompatibility complex. These are molecules that jut off the surface of the iron particle like spikes. I'll remind you that the MHC complex molecules are those that we use for organ transplant and blood transfusions, because if you don't get a good match on those, you really rev up the immune system. So the spikes on the surface of the iron particles are meant to mimic those found on the immune regulatory cells known as antigen-presenting cells, which mop up antigens all over the body and then stud them on their surface, rather like a hermit crab covering itself with little bits of shell, and then take them to the T cells and tell the T cells whether to attack or ignore these particular antigens. Santa Maria likens them to T cell bait. Another strategy that's being used in the clinic is to take the antigens in question that the immune system is reacting to and attach them to certain sugar tags that then direct the molecules to the liver. The liver takes them up, and the liver is quite important for generating immune tolerance. The liver, after all, gets first crack at anything you put in your mouth. It all goes from the gut to the portal vein, where it is basically sent through the liver, which filters it and has plenty of antigen-presenting cells that can induce inactivation or even deletion of a T cell line that is going to react to those antigens. There's a little bit of hand waving, and that remind me of that old Gary Larson cartoon of the scientist with the board full of equations, and then this empty spot where it says, then a miracle happens, and more equations extend onto the other blackboard. But if a miracle can happen reliably without us actually knowing why, I'm still content to exploit it. Yet a third approach is killing the beta cells. In this approach, it's very similar to the chimeric antigen T cell receptor therapies used in cancers. In this, the scientists take T cells and re-engineer them to express a autoantibody receptor that specifically targets them to the B cells that are producing the harmful antibodies. So this is actually kind of a search and destroy mission, very similar to what's used to get the T cells to search and destroy cancer cells. Back to Dr. Santamaria. He began working how to use those trackable T cells as therapy, and he suspected that the nanoparticles might cause the cells to die or go dormant. Back then, he was working with a mouse model of type 1 diabetes, a disease in which epitope spreading is known to occur. Your word for the day, that means new antigens are becoming activated in the immune system, or I should more accurately say that the immune system is being activated to attack bystander antigens that are present in the tissue that is being attacked by the first line of attack, those first antibodies or T cells. So he developed a cocktail of particles that carried different antigen fragments, different epitopes, and he used a nanoparticle carrying a single epitope, surmising that it wouldn't have any effect because T cells recognize thousands of epitopes in diabetes, but both the control and the experimental nanoparticles reversed the diabetes symptoms. It didn't make any sense. These were just nanoparticles. The antigens weren't on there. And it took him years to work out what was going on, but now he thinks he understands it. His current hypothesis is that the iron nanoparticles prompt T cells to multiply and morph into regulatory T cells, which travel to the site of inflammation. So it doesn't matter what's on the iron. The iron is acting as a signal to create this morphing into regulatory T cells. The regulatory T cells travel to where the inflammation is, go where the action is, and they bind and deactivate the antigen-presenting cells that carry not only the antigen that the cells recognize, but thousands of other antigens that are important in diabetes. So now these cells can no longer activate the immune cells, and you stop the vicious cycle of autoimmunity. The nanoparticle-fused antigen works as a master switch. This hasn't been tested clinically yet. We're still in mice, but Santamaria has founded a company, naturally, because that's what they all do. I'm sure they're getting plenty of venture capital because a actual autoimmune cure for type 1 diabetes would transform the lives of children and adults everywhere. So we talked a little while about the liver, and there is a key in the liver, because the liver is where all the blood carrying those foreign antigens from the gut gets filtered. It's also the destination of almost all the cellular debris left behind when cells and tissues die. So it has a great opportunity to look at what's passing through the body and an important role in establishing immune tolerance. Dr. Hubble and his colleagues discovered that the cellular debris carries a special sugar tag that directs it to the liver. And if they add this sugar tag to other proteins, they could direct just about any molecule they want to the liver, including antigens such as the myelin proteins that activate the immune system in multiple sclerosis. In 2023, they showed that this strategy works to reverse symptoms of a multiple sclerosis-like disease in mice. What's so exciting about this paper is that these animals had advanced disease, meaning that their immune systems were probably reacting against a variety of antigens, yet treatment with just one antigen worked to reverse the paralysis. There's a phase 2 trial going in people with multiple sclerosis using this strategy that will be starting soon. I'm sure you'll hear all about it when it's published. We still don't know exactly how it works after the antigen travels to the liver. Then a miracle happens. But if we can show that it works and it's safe, it's a real game changer. Yet another approach that's being tried is to take T cells from the patient's blood, extract the regulatory cells that are already there, and then engineer them to express an antigen that will direct the regulatory T cells to the site of the disease when they are re-injected. There, because they are regulatory T cells, they should be able to calm all of the angry T cells in the vicinity, not just those that recognize the specific antigen they carry. Sonoma Biotherapeutics has tested these regulatory T cells in clinical trials, but not those cells engineered to express a specific antigen. They plan to give the first dose to a person with rheumatoid arthritis in early 2024, but nothing's been published yet. Bluestone thinks that this approach is less risky than dosing people with antigens that might further exacerbate autoimmunity, and regulatory T cells produce tissue repair factors, which might actually help reverse some of the damage wrought by the disease. But cellular therapies also come with challenges, including the high cost and potential side effects. These are living drugs. How do you determine a dose for cells that, once infused, begin replicating in the body? There's a lot we need to learn. An overdose of T regulatory cells could potentially create the very tendency towards infection that we're trying to avoid by approaching autoimmune disease in this fashion. While researchers such as Bluestone and Hubble are working to prod the immune system towards tolerance, others are developing therapies to directly kill the immune cells that contribute to the disease. I would vote that the most likely one to have unintended consequences. One team in Germany is trying an approach commonly used to treat blood cell cancers that equips T cells with what's known as the chimeric antigen receptor. Then those T cells are taken from the body and engineered to express this special synthetic receptor on their surface. They can create a chimeric antigen receptor that binds to CD19, which is a protein found in all B cells. The clinicians then infuse the CAR cells into a body, and they start to attack the B cells. So far, researchers have presented results for a total of 15 people, 8 with lupus, 4 with systemic sclerosis, 3 with idiopathic inflammatory myositis, which causes muscle inflammation and weakness. People's symptoms improved dramatically, but what's most surprising is that they have all stayed in remission even after they began producing new B cells. It's as if wiping out the B cells performed a reset on the immune system. The results are mind-boggling. Outstanding, says Lawrence Steinman, a neuroimmunologist at Stanford University, who many call the father of antigen-specific therapy. The first participant in the study, who had lupus, passed the 1,000-day mark in December with no sign of disease. Koenig agrees the results are incredible. Most people would not have predicted the degree of durability. But he adds, I don't think we can expect the disease will stay gone forever in every patient. The T cells that help drive lupus are still in there. So CAR therapies target and kill all B cells, which might make it a stretch to consider the approach a way of restoring tolerance. But for most autoimmune disease, only a small fraction of B cells are troublemakers. Amy Payne, a dermatologist at Columbia University Vagelos College of Physicians and Surgeons in New York City, wanted to find a way to target just those cells. She studies a rare skin disease called mucosal pemphigus vulgaris. In people with this disease, the immune system makes antibodies against a protein in the skin called desmoglein 3. It's responsible for holding your epithelial cells together, she says. So with this antibody attack, the cells fall apart and you get blisters all through the mucosa and on the skin. The standard therapy for pemphigus, a monoclonal antibody, works by destroying B cells. With the B cells gone, the antibodies against desmoglein 3 disappear and people go into remission. Our current therapies are really a blunt weapon. Payne realized that she might be able to develop a more focused weapon by tweaking the CAR-T approach. Rather than engineering the T cell receptor that would bind to all beta cells, she could engineer the T cells to express the desmogin 3 protein, which would bind only to the desmogin 3 antibodies sticking off the surface of the rogue B cells. This therapy, known as the chimeric autoantibody receptor T cell, it's like a laser, she says, targeting the autoreactive B cells that are causing the disease, but leaving the healthy B cells alone. So, of course, Payne founded a company called Cabelletta Bio in Philadelphia and is currently testing these cells in people with pemphigus and another autoimmune disease called myasthenia gravis that causes muscle weakness. So beta cells, B cells, are emerging as a promising target in many autoimmune diseases. In some of the most common disorders, B cells have complex roles. They don't just produce antibodies, but they also churn out signals that trigger inflammation and present antigens to T cells, so helping to fan the flames that keep the autoimmune disease burning. In immunology, everyone's been focused on T cells because they were the smart ones and B cells were just the poor cousin, but maybe B cells really are the key. Stedman is careful not to be too optimistic. He's investigated decades in approaches directed at immune tolerance. Every time these are taken to the clinic, including some of my own efforts, they fall short of getting a drug approval. At this point, he says, I'm going to hedge my bets. Santa Maria suggests that many past failures stem from poor understanding of the underlying mechanisms. I think they failed because they're going into clinical testing before we actually know what the hell we're doing, he says. Now, 18 years into his research on Navasims, he thinks that his team has a good shot at success. Koenig favors approaches that involve B-cell depletion. That's the strategy that his team is working on, so he accepts that he might be biased. The beauty is that eventually we'll learn from the data exactly what the right approach is. And that, my friends, is how science marches on. And since we've been wandering all over the brain and autoimmunity, I thought that it would be good to wrap things up with some basic science research. Scientists have identified a neural mechanism that could underlie fasting-mediated immune regulation. Now, we all know that fasting, defined as the involuntary abstention from eating and sometimes drinking for a set time, has become increasingly widespread, as some studies have found that it could boost the immune system and help prevent the development of some diseases. There are now several smartphone applications on which people can record their periods of intermittent fasting and find out more about the potential benefits of fasting. Researchers at the University of Science and Technology of China recently carried out a study on mice aimed at better understanding the neural processes underlying the reported effects of fasting on the immune system. Their findings, published recently in Nature Neuroscience, suggest that fasting could specifically promote the neuronal control of inflammation and influence the distribution of T cells, a class of white blood cells that contribute to fighting germs and protecting the body from diseases. Dietary fasting markedly influences the distribution and function of immune cells and exerts potent immunosuppressive effects. Liang Wang, Mishu Sheng, and their colleagues wrote in their paper. However, the mechanisms through which fasting regulates immunity remain obscure. We report that catecholaminergic neurons in the ventrolateral medulla are activated during fasting in mice, and we demonstrate that the activity of these catecholaminergic neurons impacts the distribution of T cells and the development of autoimmune disease in an experimental autoimmune encephalomyelitis model. It goes something like this. Eating itself is intrinsically inflammatory. So, fasting reduces this so-called nutritional stress. The reduction of nutritional stress activates these orexigenic catecholaminergic neurons, and that stimulates the release of naturally occurring glucocorticoids via a neural circuit that targets the adrenal glands. A side effect of this causes the T cells to home in on the bone marrow and stop circulating in the general system, thus suppressing autoimmune diseases. In prior research, the scientists formed a hypothesis that it was the catecholaminergic neurons in a brain region known as the ventrolateral medulla that played a part in the fasting-mediated changes. To test this hypothesis, they first examined the activity of these neurons in mice that were fed regularly, and also in mice that were not fed for 24 hours. In addition, they then selectively ablated, in other words, destroyed or activated these neurons to observe how their intervention influenced other neural mechanisms, as well as the course of the autoimmune disease in mice. Ablation of these specific catecholaminergic neurons largely reversed fasting-mediated T-cell redistribution. In other words, the T-cells remained in the general circulation where they could trigger autoimmune disease. Activation of these neurons drove T-cell homing to bone marrow, which may be mediated by a neural circuit that stimulates corticosterone secretion. Similar to fasting, the continuous activation of these VLM catecholaminergic neurons suppressed T-cell activation, proliferation, differentiation, and cytokine production in an autoimmune mouse models and substantially alleviated the disease symptoms. The findings gathered by this team provide some new valuable insight into the neural mechanisms that could drive some of the previously observed benefits of intermittent fasting. As we put together the pieces, this ancient practice is turning out to be very validated by modern scientific techniques. Well, we've come to the end of another hour of Ask Dr. Dawn. I hope you've enjoyed it and learned something useful. Maybe even be a little bit inspired to engage in some time-limited eating yourself. Well, that's about all for this week's podcast. Please go to AskDrDawn.com for news about our future plans. For now, this is Dr. Dawn saying so long and stay healthy.
Ask Dr. Dawn is brought to you by Jiva Media. Production and editing by Charles Bansky. Music by John Scoville.